Okay. So today we're gonna begin with the idea of entropy. So let us consider what we had derived so far. So let's consider a reversible Carnot engine, meaning it's something which operates in a cycle which accepts heat. So this is the Carnot cycle and it rejects heat. And as a consequence, it gives you some work output. This could be W dot, this could be Q dot, this could be QL dot if it's a continuous process. But for now, it doesn't matter. We can write it as this. So for this, let us see what the closed integral of del Q for the entire process, the cyclic processes. It's essentially gonna be QH minus QL, which is a quantity which is greater than 0. Alright. Moreover, from the definition of the absolute, so this is just first law. Moreover, from the definition of the absolute temperature, we have seen that QH upon QL for a reversible process, it becomes equal to TH upon TL, where TH and TL are now the absolute temperatures. So this is from the definition of absolute scale for reversible engines or for reversible processes in general. So if this is true, then we can write QH over QL minus QH over TH minus QL over TL is equal to 0, because we can rearrange this as QH over TH is equal to QL over TL. We can always do this rearrangement, and this implies that cyclic integral of del Q over T is also equal to 0, where T is the temperature of the reservoir temperature. Okay, so in general we can conclude that for all reversible cycles, closed integral del Q is greater than 0, closed integral del Q by T is equal to 0. So this is true for reversible engines. So far is this okay? Is there any doubt in this?
So from where did the first statement come from, that let integral of del Q greater than 0?
It is greater than 0. We are analyzing a heat engine. So more heat has to be absorbed, right? In order for you to get some work output, if you apply first law for this control volume, this red control volume, what is the total amount of heat absorbed in this cycle? It's simply going to be QH minus QL.
Okay, sir. Yes.
There is nothing complicated. Don't think too hard about this. Now, with this in mind, with this little thing in mind, let us see what happens for an irreversible engine. What about irreversible engines? Let us first write down the basic idea that the work output of an irreversible cyclic process will be less than the work output of a reversible cyclic process. Why? Why is this statement true? This is true by what? By something which we have done yesterday. Now this is true by Carnot's first proposition, right? That the reversible heat engine is the most efficient heat engine, operating between what? The same temperature difference. Now if this is true, let me just draw the schematic of the heat engine over here. This is QH, this is QL, and this is W. So if this is true, then what does that mean? The W irreversible, meaning you are absorbing the same amount of heat, but you are rejecting a larger amount of heat to the lower temperature reservoir, as compared to you are absorbing the same amount of heat in the reversible, but you are rejecting lower amount of heat to the reversible. Okay, here the basic premise is QL reversible will be less than QL irreversible. But QL reversible is not zero. You have to reject some heat to the surrounding, but this is not zero. But this is the most ideal, meaning this is the minimum amount of heat you have to reject to the surrounding. Why? So that you can obtain the maximum amount of work done from the cycle. Is this statement clear?
Yes, sir.
So
Yeah.
I have one doubt, sir. So though in the case of reversible, we have to reject heat,
Hmm.
otherwise we can't do any work done.
Hmm.
So it is impossible to have a 100% efficient uh, engine.
Yes.
So, but even in the reversible,
Hmm.
like we like somehow manage to not.
You do whatever. You do whatever you want. You
Actually,
will still have to reject some amount of heat to the surrounding. And what is the lower bound on how much heat you must reject comes from concepts developed later in this course. But you must reject something to the surrounding. And
okay, sir.
for a very ideal process, how much heat do you reject to the surrounding? How do you figure that out? If this is TH, if this is TL, you can say that QH over QL will be TH over TL. If you know what TH and TL are, and you know how much heat input is there, you will figure out what the minimum amount of heat rejected to the surrounding will be. And once you know what the minimum amount of heat rejected to the surrounding will be, you can figure out what is the maximum work output of such a engine using this. This is going to be then W max of that engine. Okay?
Yes, sir.
So this is the basic premise, that more amount of heat is rejected to the surroundings, and consequently less work is obtained from the irreversible engine. Okay, less amount of work output is obtained from the irreversible engine given the same amount of heat input to the engine. So now let us rewrite these statements. What is closed integral del q? It is still greater than zero. There is, there is nothing conclusive you can say about this. But now what is the closed integral del q over t? It will be qh over th minus ql irreversible over TL. What is the sign? Now, because QL has increased, okay, because QL is QL irreversible is larger than QL reversible, meaning this negative term is larger. So, what is the sign of this overall term?
Negative.
It will be less than zero. Very good. So, it is negative. Now, I can make this engine more and more reversible. In the limit, the engine is the most irreversible engine imaginable. So for the most irreversible engine, what is the work output?
0.
Zero.
Zero.
So then what is closed integral del Q?
It will be 0.
It will also be zero, because closed integral del Q is equal to the work output. Okay, closed integral del Q for this black control volume will be equal to del Q. So for the most irreversible thing, we know that it can become zero. So del Q is greater than equal to zero. All right, and QH minus QL irreversible is less than zero. So let us combine statements 1 and 2 to write down the general statement. So del Q greater than equal to 0 and del Q by T less than equal to 0. Here the equality holds true. When does the equality holds true?
Most irreversible.
No. Look at which statement I've written.
Okay, for the second statement.
For the second statement, the equality holds true for what?
So when it is reversible.
When it is reversible. And here the equality can hold true
When it is most irreversible.
when it is most irreversible. Basically, the process is so irreversible that you are getting practically no work output. All the heat absorbed by the system has to be given back to the surrounding. It's like someone gives you 100 rupee investment and you are such a lousy investor, you give him no output and you simply have to return him 100 rupees back. Okay? That is how you can look at it if you like finances. Alright, so far so good. This is very important. Let us do the same analysis for a refrigerator. Same analysis for the reverse Carnot. And reverse Carnot engine will be simply a refrigeration cycle. Okay, so let us draw the reverse Carnot cycle. You have TH, you have TL, you have something working in a process, cyclic process, and you have some work input, and you have QL like this, rather QH like this, QL like this. Okay, and I'm by virtue of this arrow, I'm sort of drawing the direction of W also. So let us say, what is closed integral del Q? It will be what? QL minus QH. We have to account for the signs in the equations because we have not accounted for any sign over here. So what is QL minus QH? Is it greater than 0 or less than 0? Let us write down the first law for a control volume like this. So for a first law for a control volume like this, what can we write? Delta E equal to Q minus W. So this will be QL minus QH minus, so what is W? It will be minus W because it is work done on the system. So what does it mean? QL minus QH is equal to minus W, where W is now positive because the fact that we are doing work on the system, we are accounting by W positive, but a minus sign appended to that W, so that this quantity we can clearly see it is a negative quantity, this entire quantity. So QL minus QH, what is the sign of it from this analysis?
It's a negative.
It will be less than 0. Now, because it's a reverse Carnot cycle, we can again write down from the Carnot proposition that QH upon TH is equal to QL upon TL, and this is true for a reversible process, reversible cyclic process. This is true for a reversible cyclic process. And so for this reverse Carnot cycle also, del Q by T, which is equal to QH upon TH minus QL upon TL, is also going to be equal to 0. Alright, so is this clear? So for all reversible refrigeration cycles, what can we conclude? Closed integral del Q less than 0, closed integral del Q by T equal to 0. Now let us consider in the same chain of thought as we have done before, what happens when the process is not reversible, rather it is irreversible. You have some work input, you are extracting some QL, and suppose this is QH irreversible. Okay, so What can we conclude about an irreversible refrigerator? From logic, from pure logic. Irreversible fridge. So when the fridge is most efficient, what should you expect? The work input for a reversible fridge should be higher or lower?
Lower.
Lower.
So the
Lower, sir, for
work for
reversible.
a reversible fridge should be lower than the work for an irreversible fridge. Okay? So what does that mean? What does that imply? So if I write down the expression for W from here, it will be W is equal to QH minus QL. So I can write down QH reversible minus QL is less than QH irreversible minus QL. If I say that the amount of heat absorbed from the low temperature reservoir is the same, then I can conclude that QH irreversible will be larger than Q reversible. In order for me to extract the same amount of heat from the low temperature reservoir, I have to supply more heat to the surrounding than for a reversible cycle. Okay, that is the conclusion. So I am basically causing more irreversibility. So more heat transferred to system to have same heat extraction. And correspondingly, with this in mind, what can we conclude about closed integral del Q by T? So this will be del Q, QH irreversible over T minus Q, or rather, sorry, QH is the heat rejected. Sorry, QH is the heat rejected by this control volume, so we have to account for the sign, plus QL upon TL. Now, because QH irreversible is larger than Q reversible, QH reversible, what can we conclude about the sign of this term? QH irreversible is now larger. So this minus term is now larger. As a consequence, this term will be less than 0. So in the same train of thought as before, we can then easily conclude that del Q, what is it? It is still less than 0, right? And
So del close integral of del Q over T
is
less than.
less than equal to 0. Equality holds true for reversible process. Okay. And what about this statement?
No, I think equality will not be there.
Okay. So we cannot do the equality over here because it will violate the Clausius statement.
Yes, sir.
Alright. So effectively we have the same equation, but more importantly from these two things, regardless of the sign of del Q, what can we conclude about del Q by T from both these things? Let me just copy this result, because if you put it side by side, it is more obvious. So this is for engine, this is for refrigerator. What can you conclude about closed integral del Q by T from both these statements? And it is always less than equal to 0. Okay. So this particular statement is given the very famous name Clausius inequality. You might have studied this in your JE in a very odd way, where it is told you as a fact. No? Have you encountered this at some point of your life?
Yes, in J.
In JE,
Yes,
right?
sir.
And it was just told you as a as a matter of fact, right?
Yes, sir.
But it is not a matter of
So
fact.
I think in Resnick and Halliday, some explanation is like this is there.
Yeah. I mean, of course, if you follow Resnick and Halliday, then that's a completely different story altogether. But my understanding was not everyone follows Resnick and Halliday. But yes, it is obviously it is correctly mentioned in Resnick and Halliday. So if you have studied using Resnick and Halliday, fine, no problem. But I have given you a thorough sort of demo why this is true. And when does the equality hold true? What is going on, man? Am I becoming dyslexic? When is the equality true?
Reversible process.
For reversible processes. The equality is true for reversible processes. Now with this statement, we are now in a position to define the property of entropy. But before that, let's do a quick problem. A quick problem. Okay, so the problem is as follows. The problem is as follows. We have a condenser, then we have a boiler, we have a turbine, and we have a pump. And the work output is partially going to the pump. So let's see what happens to this del Q by T. Okay, let's see how we can do this. And the conditions that are given are, if I call this 4, if I call this 1, 2, 3. So the conditions are given as follows. At 1, it is given as 0.7 megapascal, x equal to 0. At 2, it is given as 0.7 megapascal, x equal to 1. At 3, it is given as 15 kilopascal, x equal to 0.9. And at the condenser, it is given as 15 kilopascal, 0.1 quality. So if I were to draw this in TV diagram, how would the process look? So note that the two pressures are 0.7 megapascal and 15 kilopascal. So let us draw the two isobars. This particular isobar is the 15 kilopascal isobar, and let us draw the 0.7 megapascal isobar. This is the 0.7 megapascal isobar. So let's go from 1 to 2. It's 0.7 x equal to 0. It goes to 0.7 x equal to 1. So this is state 1. This is state 2. Then state 3 is 15 kilopascal x equal to 0.9. So maybe it is something like this. And state 4 is 15 kilopascal 0.1. So this is state 3 and this is state 4. And this is the entire process. Okay, is it clear?
Yes, sir.
All right. So now let us do the calculation. So what is closed integral del Q by T? So in order to do that, we must also first figure out what these temperatures are. Okay, we must also figure out what the temperatures are. And I think I mentioned that the T is the surrounding temperature somewhere. Where was it? It is the reservoir temperature. But when we analyze cyclic processes like this T, when you want the heat transfer to happen across these two, this T will be considered to be the temperature at the boundary between this and this. Okay, we won't say that it's the reservoir temperature. When we say it like this, it is the temperature at this boundary. This boundary temperature is TL, this boundary temperature is TH. Okay, so this T for the case of boiler and condenser will be this particular saturation temperature. This will be TH, this will be TL. So just at the boundary of the boiler, if I consider this to be the control volume, let me do it with a different color. Just at the boundary of this boiler, just at the boundary of this condenser, this is the control volume. Okay, so this will be, so how much heat, how do you find out QH first of all? There is some QH like this. How do you find out QH? How do you find out QL? So let us analyze each component one by one. Boiler. This is 0.7 megapascal, x equal to 0. This is 0.7 megapascal, x equal to 0. What is it? 1. And QH. So if I write down the first law, steady state, steady flow for a boiler, mass conservation is trivial. So I can write what? 0 is equal to heat absorbed by system. So what is heat absorbed by system? Positive or negative? Positive.
Positive.
This plus M plus Mi Hi total, but because the kinetic energy and potential energy are not given, Hi total will simply become Hi minus Me He total minus W. But what is W? In this case, for a boiler, it's 0. So what is the QH over M dot? And because M dot I is equal to M dot E, actually it's throughout the system there is only one M dot. So we can always say that M dot I equal to M dot equal to M dot. So I'm going to divide by M dot. So QH, expression for QH is He minus Hi. And that is obvious. The specific heat added to the system will cause rise in the enthalpy. That should be obvious by now. So now, how do you find the enthalpy? He would be the enthalpy of steam at 0.7 megapascal, x equal to 1. That is Hg. Hi would be enthalpy of steam at 0.7 megapascal, x equal to 0, which is the enthalpy of the liquid or the fluid. Okay, so basically the amount of specific heat added to the boiler is HFG, is basically H2 minus H1. And what is H2 minus H1? It is simply HFG at 0.7 megapascal. Please look into the table and tell me what is this value. Steam.
So 697 for some water at
No.
1.
You tell me HFG directly.
Okay, sir.
So how do you do it? You go to the saturated pressure entries, 6000, you go to the, sorry, it's not 6000, it's 700 kilopascal. So you go to the pressure entry of 700 kilopascal, and HFG is 2066.30.
So it's 2066.
Yeah. And for those of you wondering how this has come into being, you really need to buckle up, or I will tell you which page number I've taken the property from. It's the saturated water pressure entry table, and the page number is 679 of the scanned documents that you have. and it's the entry on 679, page 679. I'm not gonna open up the book and show it to you. This you must be able to figure out. So correspondingly, what is QL now? So let us draw the condenser. So for the condenser, you have state 3, state 4, 3, 4. So 3 is 15 kilopascal, x equal to 0.9. 4 is 15 kilopascal, x equal to 0.1. So if you write down the first law, steady state, steady flow process, we can have 0 is equal to QL, right? So QL, when we show it like this, it is the just without any sign. Plus then I can write MI HI minus MEHE minus W, work done is 0. So QL is equal to QL over M dot, Q dot L over M dot will be HE minus HI. So HE is H4, HI is H3. So this will be, so what is H4? It is enthalpy at 15 kPa, x equal to 0.1. H3 is the enthalpy at 15 kPa, x equal to 0.9. So how do you figure this out? It is going to be H of the fluid plus 0.1 HFG at 15 kilopascal, and this is going to be HF plus 0.9 HFG at 15 kilopascal. So when you subtract these two, it will be simply 0.8
HFG.
HFG. Actually not 0.8, it should be minus 0.8 HFG.
Yes, sir.
Because heat is lost by the system. So what is this? Minus 0.8 into HFG at 15 kilopascal. So I'm gonna
But
go to that table again. I'm gonna look up page number.
Sir,
It's
it's
gonna,
1898.
yeah, just for the
yes, sir.
benefit of everyone, I'm just gonna tell the page number as well. It's page number 679, 15 kilopascal. HFG is 2373.14. So 2373.14 kilojoule per kg. And this product comes out to be how much?
1898.
1898.
And it should be clear that because you have not assumed any sign of QL, when we write it in this equation form, QL is absorbed by the system. So QL, it comes out to be negative. It means that actually heat is being lost by the system. So I can now write that if I put the arrow like this, then QL will be 1898. So then we can write down closed integral del Q by T is QH, or if I divide by m dot, then it will be QH over TH minus QL over TL. If I'm using this arrows as correct indicator, so this will be how much? 2066.30 divided by the TH minus 1898 over TL. So what are the TH and TL? So at 15 kilopascal, what is the saturation temperature? And at 0.7 megapascal, what is the saturation temperature? So this comes out to be 164.97 degrees Celsius, and this comes out to be 53.97 degrees Celsius. Guys, it's very easy. Why is everyone quiet? Saturation temperatures. So I will write this as 2066.30 over 273.15 plus 50. Oh, sorry. This is TH and this is TL. Oh, I have just swapped. This is okay. Okay, I've just swapped them by mistake.
So at 0.7 it is 164.
Man, what am I? I've completely lost my mind, it seems.
But at 0.7 megapascal, it is 164.9
This
degrees
is
Celsius.
164. So this is gonna be TH 164.94 degrees Celsius, and this is TL equal to 80 what? 53 point.
0.6.
You're using EES, right?
Yes, sir.
Yeah, because in the table the values are slightly off. Anyway, so TH is 164.94. But remember, when we are using such expressions, we must use temperature in Kelvin. So this is gonna be 1898 over TL. So TL is 53.6 plus 273.15. So what is the final answer? What do you get over here? I think you will get something like minus 1.0 something kilojoule per kg Kelvin. The unit is kilojoule per kg Kelvin. Okay, are you getting this? It's just using a calculator. There is nothing in this.
Yes, sir. Minus 1.08.
Now you may say that, okay, sir, I don't want to really account for this sign, blah, blah, blah. I got QL from calculation as minus this. Now, in fact, if you do not account for any that sign reversals and all, also you can do it. You have to always use common sense. When I have used the negative sign over here, I am treating QL as a positive quantity. Meaning, because I have accounted for the sign of QL, I will write this negative quantity. Ideally, this expression I could have written as this: QH over TH plus QL over TL. Because QH is absorbed by system, this entity in its totality will be positive, and because QL is lost by system, this entity in totality will be negative. Meaning this QL will now exactly account for this sign. So I can then write this as 2066 point whatever divided by 164.94 plus T absolute plus minus 1898 over 53.6 plus T absolute. T absolute is towards 73.16, and you will get the same answer. Do not make a mistake in the sign. I'm telling this time and again. When you account for the appropriate direction, it is assumed by you internally that whenever this Q will appear in any kind of balance equation, you will write it as minus QL because it is heat lost by the system. If you just blindly apply the formula, then you have to appropriately account for the sign. Is that clear? Do not make mistakes in this.
Yes, sir.
No,
Yes,
not
sir.
to you, just to everyone in this class. Apurv Bajaj, is this, sorry, Apurv Gaurav, is this clear?
Yes, sir.
Tell, tell me what I said in your own words. Just repeat it. What happened? In your own words, tell what I said.
Yes, sir. Wait a minute, sir. I'm gathering.
What is DC Pandey? Someone wrote DC Pandey. Yeah, Apurv,
Yes, sir.
what did I just say?
Sir, I did not, sir.
You just said you understood what I said. Now you are saying you did not hear what I said. Anyway, who else is there? Nikhil Dattatreya Lahane. Did you understand? That sign thing, did you understand? Nikita, Nirupama, Rahul. I'm skipping the usual people I know they have understood. Vedant Gupta. In order you have not understood, I'm gonna show it to you through some another illustration. I'm gonna show it in another illustration. Suppose heat comes in, heat goes out. QH, QL. I have drawn the sign over here. So when you do integral del Q, what do? You automatically do QH minus QL. Okay? But in general, if I do not have this schematic with me, integral del Q will be QH plus QL. But when in the problem you discover that QL is heat lost by the system, in the calculation you should naturally obtain it as minus ABC point XY. So when you put this minus ABC dot XY over here, it will be QH minus ABC dot XY. Or rather, let me put it QH plus minus ABC dot XY. If you already account for the fact that heat is being lost by the system, you will not write QL as minus ABC dot XY. You will write QL as ABC dot XY because you have accounted for the fact that heat is being lost by the system through this arrow coming out of the control volume. So when you put this expression over
Your
here,
voice
it
is
will be
breaking
QH
again.
minus ABC dot XY. Yes? Someone was saying something?
So your voice is breaking. I don't know. It's for me only or what.
No, sir, it's
Was
clear.
it's clear now?
It's
So
clear.
is this clear? Is this small thing that I just showed, is this clear to everyone? Apurv Gaurav, is it now clear to you?
Yes, sir. Yes, sir. It's clear.
Now tell what I just said.
Sir, you said that we'll have to consider what sign we'll have to take. So if we directly put the value of QL, we'll have to take the negative sign. But if we
Yes.
consider
So
that,
So you are correct. You have understood. Let me just put it in one more way. In a very complicated system, you do not know whether QL is positive, negative. You do not. You have no idea. In that case, which approach should you take, Apurv? If in a very big system, you do not know whether what the sign of QL is. This QL has to be figured out from maybe first law of thermodynamics. Then what do?
sir,
You
we
will you will use this approach
yes, sir.
because you do not know whether heat is absorbed by system. If heat is absorbed by system, whatever the sign comes here comes here. But if it is heat is lost by the system, whatever sign comes here comes here. Okay, that is the safer way. But logically, this is also correct. Obviously, both are correct. In one case, you are assigning the sign to the equation directly because you know that QL will be lost by the system. In the other case, you are not assuming anything, and QL from the first law or whatever, it will be given to you with the negative sign, or you will obtain QL with the negative sign. Okay, everyone. Harsh, is it clear? Harsh, Kshitij Katiyar,
Yes, sir.
does that make sense?
Yes, sir.
Okay. Abhiram, don't make these mistakes. I'm telling you time and again. Abhiram, Abhiram, hello. I mean, Swastika Mandal, is it clear to you? I think most of the people have just switched it on and gone somewhere, it seems. Susmita, Sayantan, I think it is clear to Sayantan and these people.
Yes, sir.
Yeah.
Sagnik, yeah, Susmita, is this clear? Will
Yes.
you make the sign mistake?
Yes, sir.
You will make the sign mistake? No, sir,
No,
right?
sir.
Ah, very good. Ritam, it should be clear. Rahul Gupta, does this make sense? This has to make sense. Actually, when you do a lot of problems, this will automatically come to you. This is for people who have not invested the time to do the problems. Okay, we take a small 5-minute break. Don't leave, don't go anywhere. When we come back, we will define entropy. We will do some problems. Don't go anywhere. We'll be right back. Okay, we're back. So let's proceed.
Yes, sir.
So now we will define finally entropy. So far what we have seen for a reversible cycle, closed integral del Q by T is equal to 0. Now let us consider the following plot. And it can be in any plane, it doesn't matter. We can do it in PV plane. Let us say you have point 1 and point 2. And you go from point 1 to point 2 in process A. You can come back to point 2 to point 1 through process B. Alternately, you can have a process C from which you can go to point 1 to point 2. But regardless of that, you can come back from point 2 to point 1 using process B. Alright, so let us write down this particular statement for the two processes. So for AB, we have enclosed integral del Q by T. This is equal to integral 1 to 2 del Q by T during process A plus integral 2 to 1 del Q by T in process B. Over here, I have not accounted for the sign of del Q by T in process B, despite heat being lost by the system. But we are writing this in its formula form. In calculation, del Q will automatically come out to be negative. Now, in process CB, so AB, BA, CB, BC, CB, let me, not AB, BA, AB 1 to 2, 2 to 1, CB 1 to 2, 2 to 1. Closed integral del Q by T. It will be integral 1 to 2 del Q by T C plus integral 2 to 1 del Q by T B. And this is equal to 0, this is equal to 0. And this is, so when it is equal to 0, it's both true for reversible process. Let us now subtract this. What do we have? Integral del Q by T A minus integral 1 to 2 del Q by T C is equal to 0. And this implies a very important fact that integral del Q by T A is equal to integral del Q by T in C. And A and C are arbitrary. No, this is not equal to 0. And A and C are arbitrary processes. A, C are arbitrary. Meaning in going from point A to point, rather in going from point 1 to point 2, it doesn't matter what the process is. Okay, it doesn't matter what the process is, integral del Q by T through whatever process is going to be the same. Okay, and if this is true, if the integral is independent of the path taken, okay, integral is independent of the path taken, what can we conclude about this? This quantity should be what?
State function.
It is a state function, but what will be the integral? Final integral will be what? How can I can write it as the difference of simply some property at 2 minus some property at 1.
Yes, sir.
Yes, sir.
And this property we define as entropy. Okay, this is the property we define as entropy. More generally, this we can then write down as integral 1 to 2 ds, and this is simply equal to S2 minus S1. So S, or rather ds, is equal to del Q by T reversible. This is what you can conclude from this. Okay, so look very carefully. S2 minus S1 is integral 1 to 2 del Q by T for a reversible process. Is this statement clear to everyone? Difference in
Yes,
entropy,
sir.
difference in entropy is that integral for reversible process. Now we have gone from cycle to process. But once we know what S2 minus S1 is, it does not depend on the path taken. Once we know what this integral is, that is, once we know what S2 minus S1 is, in going from 1 to 2, we do not care about what path is taken. So once we know what S2 minus S1 is, even if you go from 1 to 2 in an irreversible manner, even if you go from 1 to 2 in an irreversible manner, S2 minus S1 will be the same. Okay? S2 minus
So one
S1,
also.
yeah,
So like, could you move just to the above portion?
one more.
Just a bit more. So here, like, how did we conclude like this integral can be reversed? I mean, like, there has to be some rules for del Q by T to be like this should be reversed, right? Like we are writing some integral of del Q by T from 2 to 1 b is equal to minus of integral of del Q by T from 1 to 2. But like, will that be valid in all cases?
It is true for only reversible. It is true only for reversible.
Okay.
You note whatever I am writing. I mean, it is true for only reversible. It is not true in general. So, what I am saying is S2 minus S1 can be found out if you know a reversible process, you can do that integral. This integral will only give you S2 minus S1. But once S2 minus S1 is known, if I give you two state points, now it doesn't matter how you have reached that point. It doesn't matter how you have gone from 1 to 2. You could have gone there by a reversible process or some irreversible process. But once you know that state point 2 is this, S2 minus S1 will be the same for both the processes. But if someone tells you that I am transferring certain amount of heat across a boundary with this temperature, if you want to integrate this, then this has to be reversible in order for you to find out S2 minus S1. This is always true, but once this is known, once you know what state points 1 and 2 are, the difference in S2 minus S1 is the same even if you take a reversible process, even if you take a irreversible process, even if you take any process possible. Okay? Very
So
important.
sir,
Yeah.
we can even obtain S2 minus S1 from irreversible processes also. No? Can
Yes,
we
so
get
you
that?
cannot obtain it from an irreversible process. You can obtain, so listen carefully that English is very important. S2 minus S1 you can obtain from only reversible process. This you can S2 minus S1 you can obtain, like you can calculate from integration only using reversible process.
So, like if the process is irreversible, then S2 minus S1 we cannot calculate.
You cannot
That's
calculate, but if someone has given you that
S2 minus
I
S1.
know that S2 minus S1 is this for a reversible process, you can immediately say then S2 minus S1 is also the same for an irreversible process.
So like
What
converse
is the
is not
difference?
true.
What is the difference? Let me also write this. This is not equal to integral 1 to 2 del Q by T irreversible. But these two are still equal. These two are still equal. And because it is not equal, the equality is maintained through the irreversibility manifested through entropy generation. This idea we will come back later. Okay? This is that key idea that will give us the irreversibility, the measure of irreversibility. This thing is not equal. In going from process 1 to 2, closed integral del q by t for a reversible process is not equal to integral del q by t for an irreversible process. But in going from 1 to 2, if someone says I have no other means to find out the change of entropy, you can say, okay, because I have the reversible process, I can find out the change of entropy, the difference in entropy between state 1 and 2 using this formula. But once I have found this out, I can say that because of the irreversibility, when process goes from point 1 to point 2, when the process, it goes from point 1 to point 2, I will still have this as true, but this will not be equal to this entity. Is that clear?
Yes, sir.
No, you ask. Whatever doubt you have, you ask. We will walk it through. So no one has any doubt?
No, sir.
Okay, that's good. So let's do some problems. Okay, moreover, okay, just S is now a state property. And if you look into the table, so now let me take some screenshots of the table. You will see that now S is also tabulated. One moment. Let me share my entire screen. Entries for which table is this? A. You will now have entries for entropy as well. Look at this. What do you see? Can you see the screen properly?
Yes, sir. Yes, sir. Assumption.
So now entropy also appears as a property. So what basically happens is you are given that there is a pipe, there is a valve, and it's flowing like this, and there is some throttling going on process 1 to 2. So then find out the change in entropy. You can do the change of entropy. What if someone were to say that in this throttling process, what is the expression for this change of entropy? Then you're lost. Because for the throttling process, you cannot have this going on. You cannot have this going on. You do not know what del Q reversible in this throttling process. Throttling process is irreversible. So this you will not be able to find out. But how is then this found out? How is the S2 minus S1 actually tabulated? How did someone actually do it? If there is no way for me to find out in this throttling process how this reversible integral is found out, I cannot do this integration. There is no way for me to find out this integration. I don't know why I'm writing closed integral. It is simply the integral. Have I written down closed integral everywhere? Oh no. No, okay, that's fine.
No, sir, it was integral.
So there is no way for me to know this. I cannot do this. Cannot do. I do not know.
So we can assume a reversible process between state 1 and 2
Exactly. So
and to
now
find
that
it.
you know state 1 and 2 in whatever space, You have to now imagine that in going from state 1 to state 2, you are constructing some reversible process, either reversible heat transfer, then reversible expansion. Then you have to imagine some constructed process which will take you from this state point to this state point. It is not that throttling process. Maybe the actual process is this, but you cannot do that. You cannot do the integration. So you have to imagine this imaginary process which will take you to state 2 from state 1. Then you have to do integral del q by t for that imaginary process. Then you will find out S2 minus S1 for that imaginary process. Then you will conclude that because S2 minus S1 is now known through that imaginary process, it does not matter if I go from state 1 to state 2 in that imaginary process or in the actual process in some any other process. As long as I go from state 1 to state 2, S2 minus S1 will be fixed. Is that now clear? Is the logic now clear?
Yes, sir.
Now, if someone says
So,
that, yeah,
so I have one doubt regarding the S2 minus S1.
hmm,
So like we know the difference between S2 and S1.
hmm.
Like maybe like scientists have did for all the processes and they have find the difference. But sir, how they will find the exact S1 absolutely? Or sir,
So
is there
no,
taken
no,
from the
good question, good question, good question. Now the question is, they are entropy values that are tabulated, no problem. But they are all actually with respect to some offset, s at some point minus some offset. This offset is arbitrary. And for pure substances, crystalline substances, is not is zero at absolute zero. And this follows from the third law of thermodynamics. Okay? But it does not matter what this is, because you will never ever in any problem that you do or in any physical process will you deal with absolute entropy. You will always deal in differences in entropy, and hence this offset does not matter. Actually, this is true for all state properties. Even enthalpy, you will always deal with differences, or internal specific internal energy, you will always deal with differences. You will never deal with absolute quantities. And because you're never dealing with absolute quantities, the offset for the tabulated values in the book, or the offset in a software like RefProp, or the offset in a software like EES, it is all different. But regardless of that, you will always see that the difference is always remaining the same.
Okay, sir.
Does that answer your question? Okay.
Yes, sir.
So now entropy is also a property, so we can do the same thing. If you have two state points like pressure, temperature, you can find out the entropy if it's superheated. If you have pressure and quality, you can find out the entropy. And the entropy formula, once again, it remains the same. It is S is equal to S of the fluid plus X times SFG. It's the same thing. Okay? And typically in industries and all, when you are doing such problems, you often refer to the process diagrams in the TS diagram. So the TS diagram, and if in industry, it is very, very useful to also have the HS diagram, enthalpy versus S diagram. So now these are going beyond PV plots or TV plots. You have now incorporated entropy as a useful parameter. Okay, and this kind of diagram is known as the Moliere diagram. So let me show you how a Moliere diagram looks like. This is the psychrometry diagram. This is pressure enthalpy diagram. This is also pressure enthalpy. What is this? Temperature entropy diagram for water. So this is the TS diagram for water. And basically the scan quality is not so good. even in this diagram you have the dome. I don't know whether you are able to see this dome is there.
Yes, sir.
And there are constant volume lines. Let me just take a screenshot of this because it's
So
super
is
difficult.
this dome is for particular temperature or because
No, how
I'm
can
able
it
to
be
see
for
only
temperature? Temperature is on the y-axis.
sorry for particular pressure.
Isobars are also there in this plot.
But so there is a, I'm able to see a single dome. There are many.
Yeah, so
Sir, I
it,
think constant quality lines are also there in that graph.
constant quality is also there. Man, you cannot see anything in this. Constant enthalpy lines are also there. These are the constant enthalpy lines. These are the constant superheat lines, constant volume lines, constant quality lines. Okay, regardless of that, I will tell you how they look like. I mean, don't have to guess it. But I mean, yeah, I mean, you can imagine that in a diagram, all this information are known, and you can, when you're solving problems, you can simply say my initial point is here, my final point is here. Or if you say that it goes in a constant enthalpy process, initial point is here, final point goes in this curve, which is the constant enthalpy curve. So the difference in entropy is simply the difference in the x-intercepts or the x projections. This is now going to be the S2 minus S1. But anyway, I mean, when you do problems, it will be even clearer. So let me just tell you how in a TS diagram, the constant pressure lines look like this. Okay. In a TS diagram, and there is some critical pressure where it misses the critical point. Okay, is that fine? This is how the TS diagram looks like. Nothing complicated about it. Constant volume lines and all, don't worry too much about it, because in the problems you will do the calculations and you will find everything out. So let's finally wrap everything up. So entropy change for a reversible process. Okay, so now let us look at this. S2 minus S1 is equal to, going from 1 to 2, del Q by T reversible. This you still have. This is always true. Actually, this should not be small s, because I am writing capital Q over here. This should be capital S. Okay, capital S is the total entropy, and small s, which is capital S over small m, is the, what do you call it? Something entropy.
Specific.
It's the specific entropy. Okay, so what is this going to be? S2 minus S1 for 1 to 2. So let's say uh, you have the same schematic. You have a cyclic process. You are giving some work, rejecting heat, gaining some heat. And effectively it is the same boiler, turbine, condenser, pump. Okay, so in going from 1 to 2, what is S2 minus S1? It is going to be equal to QH over TH. Okay, S2 minus S1 is going to be equal to QH over TH. And what is, this is 3, this is 4. What is S4 minus S3? It's going to be
QL by
minus
TH.
Sir,
QL upon
QL.
TL.
QL over T. Okay, so now if I were to plot this diagram on the TS diagram, we have not yet considered what 2 and 3 are, but in these processes, this is S1, this is S2, and this temperature is going to be the TH. Okay. Now what about this turbine? What about the turbine? It's a reversible turbine. Suppose it's a reversible turbine. Not suppose, we are considering the Carnot cycle. So for a reversible turbine, what is S2 minus S3? Or what is S3 minus S2? Or S3 minus S2? It will be integral Q by T, del Q by T reversible. But if it's a adiabatic turbine, what happens?
0.
So this will be 0. So for reversible adiabatic turbine, S2 minus S1 is 0, and we say that the process is isentropic. Isentropic. Okay, so reversible and adiabatic, they imply isentropic. So in going from 2 to 3, because you have expansion, the temperature will reduce. So you're over here. So this is S3. S3 is equal to S2. Moreover, for a pump, it's an adiabatic process, it's a reversible process. So S1 is also going to be S4. And why have I drawn it at the same level? Why have I drawn them at the same level?
So Q is 0, so S3 equal to S2 and S1 equal to S4.
S4 is
Okay.
equal to S1, that is true, but why am I drawing it at the same horizontal level?
So temperature is constant.
Temperature is constant. So this is the TL temperature. Okay, so this is the entire cycle now in the TS diagram. Okay. Whereas in the TV diagram, we saw that it looked something weird. In the TV diagram, you have these lines going sideways and all. But over here, everything is nice and straight. For an ideality, of course. Now, we've already obtained this. So S2 minus S1 is equal to, from this figure, S3 minus S4. Right? So QH over TH from this equation, S2 minus S1 is QH over TH, and S3 minus S4 is what? QL over TL. Okay, I'm using small s, so it is perhaps better to use small q. Specific quantities. So what is S3 minus S4? QL over TL. So then from this, what can you conclude? QH by TH minus QL over TL is equal to 0. Have you seen this somewhere?
So yes, so initially closed integral of delta Q by T is 0 for reversible.
This is true for reversible. And what we have considered is a reversible Carnot engine. So everything checks out. Whatever we have derived so far, it sort of checks out. So now what is the net amount of heat transferred? Net amount of heat transferred. So we have QH equal to TH into S2 minus S1 from this equation. And you have QL is equal to TL into S3 minus S4. So what is the total amount of specific heat? It will be QH minus QL. So this is TH S3 minus S2 minus TL S3 minus S4. And this is what? So S2 minus S1 is S3 minus S4. So this becomes S2 minus S1 times TH minus TL. So TH minus TL times S3 minus S2 or S2 minus S1 is this area. So the area under this curve in the TS diagram is the total heat transferred. And it is also the total amount of work done for this reversible process. If I want to not deal with specific quantities, I could have written this as QH is equal to TL S2 minus S1 and QL equal to TH TL S3 minus S4. And this is also equal to what? This is TH into mass or rate of mass, depending on what is going on, times S2 minus S1. We have just used this specific definition, nothing else. Okay, is so far so good?
So the area can be called as the specific heat transfer.
Yeah,
I
yeah, it is true. It is a total, oh no, total specific heat transfer. Like net, now again, let's not call it total, it's the net specific heat transfer. And it is also the net specific work. So once you obtain the net specific work, how do you find out the total work? If you know the net specific work, how do you find out the total specific work?
multiply my mass. In
Multiply
this
by the
case,
mass flow rate or multiply by the mass. Okay, good. That's what you were trying to say, right?
yes, sir. I was telling to tell.
Okay.
I was trying to tell mass flow rate.
Yeah, that is correct. So let's do a problem. Let's do a problem. You must be thinking, ये कितने problem है इसके? But you know, you have to do it. Let's do example 8.1. A very pertinent example. Consider, so the problem statement says, consider a Carnot cycle heat pump. What is a heat pump? The heat pump is just a refrigerator where the desired output is something else. So in a refrigerator, what goes on? W dot is the work input, QL dot is heat extracted, QH dot is the heat supplied. So in a refrigerator, what is the output that you desire?
QL dot.
QL dot is the output that you desire. So you have some work input and you have some QL that is extracted, but in a heat pump, it is QH dot that is desired. This is desired. Okay, in cold countries, this is the hot space that you want to maintain, and outside in the cold countries, it is very cold. So you do work on this in this cycle. You extract some heat from the surroundings, which is already very cold, and you give some amount of heat to the hot space. So they are called as heat pumps. So in those New Zealand matches, India New Zealand matches, or any New Zealand match, you will see a lot of advertisements of Fujitsu heat pumps, because in those cold countries you must install heat pumps. Has anyone seen this, or is it just me who keeps an eye on these weird things going on? I saw that, so it just struck me. So then, for a heat pump, how do you define the efficiency of a heat pump, or rather the coefficient of performance of a heat pump? What will be this? Coefficient of performance of a heat pump will be how much? What do you think it will be? The desired outcome, what is the desired outcome? QH dot
By
and what?
W dot.
By W
By
dot.
W dot.
Very good. So this is just I'm just defining what a heat pump is. This is not the question, but I just thought you should know this. Let's just put it on the side. This is a heat pump.
So, sorry, sir, I didn't get how it is Q dot S. We have desired to take heat from lower reservoir. So
No,
it
this
should be
is
Q
not
dot S.
what is desired. This is not what is desired. It is desired to pump heat into the hot space in the house. You want room heating in the house in cold countries.
Acha, acha,
Uh,
acha.
this
We
is
need
true for
hot
cold
temperature
countries.
in room.
Yeah, you need hot temperature inside.
Okay, okay, okay.
In hot countries like ours, we need cold temperature inside.
Yes, sir.
So it is given that a Carnot cycle operates like a heat pump. So in this entire process, what is going on? Heat is absorbed into R134. So the working fluid is R134A, is a common refrigerant. Okay, so we have the low temperature reservoir 0 degree Celsius, or the boundary between the heat exchanger and this. It is given that the high temperature reservoir is 60 degrees Celsius. So heat is absorbed into the R134A at 0 degrees Celsius. Okay, so you have some heat exchanger. So basically condenser or other evaporator. Heat is absorbed. Then you have the compressor. Then you have the condenser. And then you have the throttle valve. But here it is not given as throttle valve. It is simply like a turbine, because it's all reversible. Throttle valve is irreversible, huh? So one must use reversible components. Actual processes you cannot do it reversibly, so people connect throttle valves. So let's call this 1, let's call this 2, let's call this 3, and let's call this 4. In fact, let me just draw it as, let's call this 4. So this is what is given. So it is given that it changes phase when it absorbs heat. It changes phase from two phase to saturated vapor. This is what it is given. It changes phase from two phase state to saturated vapor. So point 1 is x equal to 1 at t equal to 0. And it is given that the heat is rejected from R134A at 60 degrees Celsius, so that it ends up as saturated liquid. So it is given that point 3 is x equal to 0 at t equal to 60 degrees Celsius. Let us draw the process in the TS diagram. So in the TS diagram, the first task I should do, I mean, of course I can draw the dome, no problem. This is the dome. I then have to draw the two important lines. The two important lines are 0 degrees Celsius. So let's say that this is 0 degrees Celsius, and I will draw the t equal to 60 degrees Celsius line. So these two lines are, this is the 0 degree isotherm, this is 60 degrees Celsius isotherm. Now it is said that the input into the compressor is x equal to 1. Okay.
So
And
excuse me.
yeah,
So does TS graph also have a dome?
yes, it also has a dome. It also has a dome. In fact, I will draw the process in the PV diagram also, and then you will see how it looks.
Yes, sir.
So this is the point 1, x equal to 1, t equal to 0. So this is state point 1. Then it gets compressed to state point 2. So it goes to this pressure. Because it's given as a Carnot heat pump. Okay, so this is the, so what is process 1 to 2? It's the compression, but what is it? It's reversible
Adiabatic.
and adiabatic. Now 2 to 3 is a condenser. So in a Carnot cycle, what is the heat exchanger, the way the heat exchange occurs? Isothermal. Right? So it goes from point 2 to point 3, which is x equal to 0. So this is point number 3. So this is the second process. Now look, going from point 2 to point 3, it's actually losing enthalpy. In going from point 2 to point 3, if the fluid is losing enthalpy, then which is the direction of heat transfer? See,
So
if the
heat is
if
out
the
of the
fluid
system.
here has a higher energy and here it is lower energy, then heat must be rejected to the surrounding, right? So this
Yep.
is the
Yes.
direction of QH. Now 3 to 4. What is 3 to 4? It's a turbine or an expander. So it's reversible adiabatic. So it comes down like this. So this is point 0.4. Now point 0.4 to point 0.1. It is the isothermal heat transfer. Now, in going from point 0.4 to point 0.1, if the energy of the fluid is increasing, then what must happen?
It is taking
Definitely
in heat.
heat has to be given to the system. So this is QL. So this is QL. Okay, is that clear how to draw the schematic for such kinds of processes? Everyone?
Yes, sir.
So now the question is as follows. Find pressure after compression. So far we have drawn the schematic without even knowing what the question is. So this skill you should have. You must be able to draw this without even, bothering with whatever they have asked. Find the pressure after compression, before heat rejection, what is the pressure, and what is the coefficient of performance. These are the questions. So let's do it. Options, preferences, font size 18. Okay. So what is point 1? Let's see. Point 1 is, so I can say x1 equal to 1 and t1 equal to 0, isn't it?
Yes, sir.
So then I can say S1 equal to entropy at of R134A, T equal to T1, X equal to X1. What can I say about point 2? What can I say about
So
point 2?
x2 should be 100.
The S2
Like
is
if
equal
I
to
So let's do it. About point 2, for process 1 to 2, I can say S2 is equal to S1 because it's a reversible adiabatic process, and I know what T2 is 60 degrees Celsius. So for state point 2, I have two independent properties, so I can figure out all the other parameters of the system. So I will say S2 is also equal to S1. I will say T2 is equal to 60 degrees Celsius. Then what can I do? What is the question? Find the pressure after the compression process. So 1 to 2 is the compression process. So I must figure out what the pressure at 2 is. So P2 is pressure R134A, T equal to T2, S equal to S2. Run this and we obtain a P2 of 1467 kilopascal. P2 is equal to 1467 kilopascal. In the book it is given as 1487 kilopascal. That's okay. Small percentage error, no problem. Kilopascal. Okay. Then what is going on? What is the pressure before heat rejection? So the question is, what is pressure at point 4? What is the pressure at point 4? That's what they're asking. Now, how do I know what the pressure at point 4 is? We will first see what point 3 is. So point 3, x3 is x equal to 0. And what is T3? 60. So I can find out what S3 is. So it is the entropy R134A T equal to T3, X equal to X3. Run this, no problem. What is process 3 to 4? 3 to
Yeah,
4?
but heat rejection is occurring in condenser, no?
It is of, but I don't know how to pinpoint what point 4 is. So for that I need to first find the entropy of 3, because at point 4 S4 is equal to S3 and T4 is equal to 0 degree Celsius. I have no other way of finding out an additional parameter with which I can pinpoint exactly what state point 4 is.
So what I mean is that heat rejection is occurring from process 2 to process 3, no?
Sorry. Yes. You are correct. Before the heat rejection, we have already done. Oh, sorry, pressure after compression and before the heat rejection. But heat is being rejected at this. So P2 and yeah, so they are the same. Okay, so let me just modify the question. Actually, pressure just after compression is the same as pressure just before heat rejection. So let's say before heat absorption. You are correct. Okay, let us try to find out the pressure at point 4. So for 4, what will I write? S4 equal to S3. I will say T4 is equal to 0. And I will say P4 equal to pressure R134A, T equal to T4 and S equal to S4. Let's run this. So P4 is 293 kilopascal. Okay, so let me just draw this schematic in a slightly bigger manner. So if I were to draw the isotherms, okay, so okay, once again inside the dome, because temperature and pressure are fixed, so the isobar inside the dome is also the same thing. So this is the isobar. So this isobar is what? 200 and how much? 293 kilopascal. But what do you think? Is point 2 and point 3 on the same isobar? Is point 2 and point
No,
3 on the same?
no, sir.
No, sir.
How does the isobar of point 3 look like? The isobar of point 3 will be something like this. Okay. The isobar of point 3 will be something like this. Whereas, how will now the isobar of point 2 look like? The guy who just pointed out that small mistake, tell me, how will the isobar look like for point 2?
So it will be between both of them.
Between both of them. Very good. What is your name? You have also understood the subject, it seems.
Adarsh
Adarsh.
Sharma.
Adarsh. I have to guess. Okay. Now, so you expect the pressure at point 3 to be higher than the pressure at point 2. What is the pressure at point 2? 1467 kilopascal. For our own verification purpose, let us see what the pressure at point 3 is. So over here I can simply do P3 equal to pressure R134A, T equal to T3 and X equal to X3. So P3 is 1683. So this is the 1683 kilopascal isobar. Are you convinced now how the isobars look? Anyone has any doubt in this, whatever I've drawn so far, whatever I've shown so far? Let us look at the last part of the question. What is the coefficient of performance? We want coefficient of performance of the heat pump, that is QH over W, which is effectively QH over QH minus QL. So how do I find that out?
So we need to use entropy at different points. Like,
You can do it that way. You can do it that way. I mean, of course, you can brute force calculate QH, QL, and you can do it. But come on, it's a Carnot cycle. How do you figure this out?
So just TH upon TH minus
Very
TL.
good. Very good. It will be TH over TH minus TL. And we will verify this. We will actually then go ahead and find out QH, QL, and we will do this. Okay. Just for everyone's, you know, sake, we will do it. So this is TH is how much? 60 degrees Celsius is 273.15 plus 60. And what is QH minus QL?
60.
60. So what is this? What is this fraction? 5.5 something, no? In the book it is given 5.5. Okay, 5.55. Now let us undertake the task of finding out what QH is. Now, what is QH? What is QH in this? Heat is lost by the system. So QH will be equal to the enthalpy at 2 minus enthalpy at 3, because the fluid is losing enthalpy and that is manifested as QH. Or it is also equal to TH into S2 minus S3. These two should be equal. Let's see whether these two are equal. So QH evaluated using process 1 is H2 minus H3. What is H2? It is the enthalpy of R134A at T equal to T2, S equal to S2. What is H3? H3 is the enthalpy of R134A at T equal to T3, X equal to X3. So what is QH1? QH1 comes out to be 144.6 kilojoule per kg. So this is 144.6 kilojoule per kg. Let us verify whether QH1, so let me call it QH2, it is equal to the absolute temperature, that is TH, that is, what is TH? 60 degrees Celsius, right?
60 degree.
So I can write T2 plus 273.15 times S2 minus S3. Okay, let's run this. So QH2 is 147.3, and this offset is because of this, not exactly, I have not taken this exact. Okay, this offset is not the exact quantity, that is the only difference. All right, so don't think that these two are very different. Okay, what else should we calculate? QL is the difference in enthalpy of, so what should I write for the expression for QL?
So T1 plus 273.15 into.
No, so I mean, in terms of enthalpy, what is QL? If you apply the first law for process 421, which is a steady state, steady flow heat exchanger, it will be
So
what?
it's H1 minus H4.
H1 minus H4. So let us write it as this. It is H1 minus, sorry, H1 minus H4, where H1 is the enthalpy of R134A, T equal to T1, X equal to X1, and H4 is enthalpy of R134A, T equal to T4, S equal to S4. And let me call this QL1. QL2 is the T1 plus 273.15 times S1 minus S4, where S4 is the entropy of R134A at T equal to T4. Oh, S4 we already have. S4 is S3. And S1 also we already have. So, okay. So, that's it. When we run this, QL1 is 120.8, QL2 is 120.8. So this small difference in QH1 and QH2, I will attribute to the small errors accumulating at the enthalpy scale. I don't think it's due to this at all. Is this expression correct, guys? T equal to T2 S2, yeah, and T equal to T3, and X equal to X3. X3 is what? 0. Yeah, that's fine. Ideally this should have been equal, but no problem. They have a small percentage error. You have to deal with it. So now we have QL was, how much was it? QL was 120.8. Apurv, is Apurv there?
Yes, sir.
Now tell me, if I have over in all these processes I have accounted for the sign. What should be the, if I do not account for the signs, what should I write QH and QL as? If I do not account for the sign, look at this diagram and tell. Heat is absorbed by system. What is absorbed by the system? It is transferred to the system. QL.
Yes, sir.
So what is the sign of QL?
Absorbed by the, sir, plus sign.
Very good. So this is kilojoule per kg. And QH is the heat lost by the system. So what should be the actual sign of QH?
Negative sign.
So minus 144.6. Why am I writing it like this? Because if I can then write down for a cyclic process 0 is equal to Q minus W. For a cyclic process I can write this. So W, so summation. So W is summation Q. So what is summation Q? It will be QH plus QL. So what is this? What is QH plus QL? Apurv.
Yes, sir. QS plus QL is minus 144 plus 120.
Tell me the value.
24.2.
So what does the minus sign indicate to you, Apurv?
Yes, sir. Minus 23.8.
ठीक है, minus 23.8. What does the minus sign indicate to you?
It is negative work is done.
What is it? That I can understand. Negative work is done. What does it mean?
Negative work is done means work done on the system.
So you have to give work input to the system.
Yes, sir.
How do you give work input to such a system, such a heat pump?
Energy source.
What is the? Come on, man! Don't say this kind of answers in a Viva. What is the energy source? Heat pump, a commercial device that you can install in your home in cold country.
Sir,
How do you give heat? Do you do a bicycle? Do you run a bicycle?
electrical
Electricity. Electrical energy. You should say this. Electrical energy goes into a electric motor which rotates the piston pump.
Yes, sir.
Okay? Compressor. This you should say. Don't say energy source. What is that? It's not the sun. Okay, so this is the amount of work input that the system requires. So now, what is the coefficient of performance of this heat pump?
Q by W.
Which Q?
Which Q? QL.
No.
Sorry. Q H minus QL.
Adarsh, tell the answer.
So it should be QH upon QL, QH upon QH minus QL.
So what is it? Tell us the value.
It will out to 5.07.
What is it?
5.07.
5.07.
Oh,
Why
sir,
is
sorry,
there
sir. So,
such a large discrepancy?
it,
Tell.
it,
Sir,
it
it's
is
coming
5.07.
6.075.
6.
6 point something.
Yes, sir. 144.6 divided by 23.8 is coming out 6.075.
Yes, sir.
That's a lot of difference. Actually, the ratios, because the small changes here will manifest in large ratio changes. So what is the answer you're getting using this approach? Weird. 100 and what? No, not 100. Come on. What is this? Let me open up my calculator. No, so you tell me the answer, what you're obtaining over here. 6 point?
So 6.075.
075. Okay, what can you do? This should have been equal to this ideally. Okay?
But so
Hmm?
by the temperature, it is coming out like 5.55, which is very.
It is varying. This is unexpected.
So is it due to?
At this small difference, it is due to this.
Okay.
Why
But
is it?
even if it takes a 147.3, then it will come large.
No, when you make this 147, then the denominator will also change. Achha, do it for 147. 147 point, what is it? 147 for 147.
No, sir. It's 5.55.
Yeah, that's what I'm saying. If
Yes,
you
yes.
see what is
We have
happening,
discussed.
small change in QH and big difference in denominator always tends to magnify that ratio. Here it is always going to be small number. So small change over here will really drastically change the final answer. Do you understand?
Yes, sir.
My question is, why should there be this difference at all? Mm, okay, I'll look into it. But anyway, I mean, there's nothing to be worried about. When you're given a Carnot, you should try to use the shortcut that it's going to be proportional to the temperature, absolute temperature. So now let's also draw this process on a
So,
PV diagram.
sorry, sir,
Yeah.
to interrupt, but sir, we have another class, and so that
Just one
professor.
moment.
Yes,
Just one
yes,
moment.
sir.
I'm just showing you how the process will look like in the PV diagram. So in the PV diagram, the isotherm is like this. So this is the 60 degrees Celsius isotherm. This is 0 degrees Celsius isotherm. And on this is state point 1. Compression occurs and you go to state point 2 because compression is occurring, the volume reduces, specific volume reduces. So this is 1, this is 2, this is 3, and 4 is something like this. Okay, this is how the entire process looks like. So this is 0 degrees Celsius, this is 60 degrees Celsius. Process 1 to 2 is the what do you call, adiabatic
Isothermal.
reversible. It's the isentropic. No, 1 to 2 is not. 1 to 2 is definitely not anything else apart from isentropic. So this is isentropic and this is isentropic. Okay, isentropic. This is isentropic. 2 to 3 is what? What do you say about 2 to 3? It's isothermal. And 4 to 1 is also isothermal. Okay, now I'm
Yes,
done
sir.
with this. All the very best for your exams. I will give more practice problems over the weekend. Please find time to do those. It's for your own good. Okay, I will be sharing this. I have put all the files in the file section. Videos will be uploaded. All the very best. Go to your next class. See you.
Thank
Bye.
you, sir.
Thank you, sir.
Thank you, sir.